3, 2, 1. We have ignition and we have liftoff.
In 1977, Voyager left Earth on a mission expected to last only 5 years. Yet it is still operating, still sending signals from the edge of the Sun's sphere of influence. Gone are the spectacular images of Jupiter and Saturn, replaced by faint streams of data arriving from a place no spacecraft had ever reached before. Where the solar wind slows down, cosmic rays intensify, and interstellar space begins to emerge. The edge of the solar system is not a clearly defined boundary, but a region where the Sun quietly collides with the rest of the galaxy. But what exactly has Voyager discovered in that distant darkness? Hello, and welcome to Astrexo. This is the journey to the Sun's final frontier. Before Voyager 2 could verify that boundary region, Voyager 1 had already ventured ahead into an area that made scientists far more cautious than they had originally expected. As the spacecraft approached the edge of the heliosphere, particles originating from the Sun began to decline sharply, while cosmic rays from beyond increased noticeably. This was the first sign that Voyager 1 was no longer deep within the protective region of the solar wind. But the problem was that the magnetic field did not change direction as dramatically as many models had anticipated. If the heliopause were a simple boundary, the transition should have been more obvious. Yet the data showed that Voyager 1 was passing through a complex transitional region, where the signs did not appear all at once. Because Voyager 1's direct plasma instrument had stopped working long ago, the mission team had to rely on the plasma wave subsystem to listen to oscillations in the plasma surrounding the spacecraft. When those oscillations revealed a plasma density far higher than that found inside the heliosphere, NASA finally had enough evidence to confirm that Voyager 1 had crossed the heliopause on August 25, 2012. What made this especially remarkable was that the spacecraft had crossed that boundary before scientists could say with certainty that it had done so. And that delay itself revealed that the edge of the solar system is not a thin line, but a boundary region made up of multiple layers of data that must be interpreted carefully. If Voyager 1 marked humanity's first crossing beyond the Sun's boundary, then Voyager 2 provided the verification that made the picture far more certain. 6 years after Voyager 1, the remaining spacecraft continued outward along a different path and carried one crucial advantage. Its plasma instrument was still operational. This turned Voyager 2's crossing of the heliopause into a rare opportunity, because scientists could not only infer the interstellar environment from changes in high-energy particles, but also directly measure the plasma surrounding the spacecraft. On November 5, 2018, Voyager 2 crossed the heliopause. What made this milestone special was not simply that Voyager 2 became the second human-made object to enter interstellar space, but that its plasma science instrument was still operating when it crossed the boundary. As a result, scientists were able to directly measure changes in the plasma instead of relying solely on high-energy particles and plasma waves, as they had with Voyager 1. This is why Voyager 2 was not merely a repeat of Voyager 1, but the second piece of the puzzle that allowed researchers to examine the Sun's boundary region from a different direction. The stream of particles carried by the solar wind dropped sharply. The plasma environment outside became denser, and the data showed that the spacecraft had left the region where the Sun still controlled the flow of particles. No image marked that moment. No wall appeared before a camera lens. Yet in the data, the transition looked like a door quietly closing behind Voyager 2. Inside was the heliosphere. Outside was interstellar space, What mattered most was that Voyager 2 did not simply confirm Voyager 1's journey, but also revealed that this boundary is not the same in every direction. Voyager 1 and Voyager 2 left the heliosphere along two different paths, one north and one south of the planetary plane. And their data showed that the heliosphere is not a perfect sphere, but a structure distorted by the sun's motion and the surrounding interstellar environment. The heliosphere resembles a bubble drifting through a stream rather than a stationary sphere, because the sun itself is moving through interstellar space and carrying its entire sphere of influence with it. Solar activity also changes in cycles, meaning that the solar wind, magnetic field, and the number of particles flowing outward are never completely stable. As a result, the edge of the heliosphere is not a fixed shell. It contracts, expands, fluctuates, and responds to waves of energy propagating outward from within. A single measurement provides only a slice of the picture, but two spacecraft traveling in different directions began to reveal the true nature of the boundary region. It has depth, turbulence, and smaller hidden structures within it. One of the most intriguing ideas to emerge from studies of the heliosheath is the existence of magnetic bubbles. In a simplified view, the sun's magnetic field extends outward along relatively continuous lines, like strands being carried away by the solar wind. But when the solar wind slows down and becomes compressed near the outer boundary, magnetic field lines can become twisted, stretched, and reconnected. This process may create closed magnetic regions, resembling small bubbles embedded within the outer layers of the heliosphere. If this is correct, the heliopause does not resemble a flat shield. It is more like a vast sea of magnetic foam, where high-energy particles can become trapped, redirected, or find pathways into the interior. This is important because the heliosphere is not merely a geometric boundary. It is part of the protective environment that shields the inner solar system from a portion of the high-energy cosmic rays originating throughout the galaxy. If the sun's outermost boundary has a complex structure, then the way cosmic rays enter the heliosphere is far more complicated as well. They are not simply blocked or allowed to pass through, but can be bent by magnetic fields, scattered throughout the heliosheath, influenced by magnetic bubbles, and altered by the sun's activity cycle. Voyager allowed humanity to see this through real data. Not through simulations, not through distant inference, but through measurements taken at the very place where these processes are unfolding. We often picture the solar system through its familiar planets, but Voyager revealed that it also possesses a much larger invisible layer, the plasma shell created by the sun. Inside that shell, the planets exist within the environment of a star. Beyond it, the galaxy begins to impose its own conditions. If the planets are islands within the sunlight of our star, then the heliopause is the most distant shoreline of the ocean the sun has created. Beyond the heliopause is not emptiness, but an extremely diffuse environment that still contains plasma, dust, magnetic fields, plasma waves, and high-energy particles arriving from across the galaxy. A cosmic ray passing through Voyager may have been born in a stellar explosion thousands or even millions of years ago. A plasma oscillation detected by the spacecraft's instruments may be the result of a burst of solar activity that took a very long time to reach the outermost boundary. A subtle change in the magnetic field may contain clues about how the sun is being compressed by the surrounding interstellar environment. This is what makes Voyager different from most planetary exploration missions. When it flew past Jupiter and Saturn, Voyager returned images of clouds, storms, rings, and moons. But at the edge of the heliosphere, there are no surfaces, no clouds, and no planet for a camera to point toward. The most important things there are invisible, and Voyager had to turn the invisible into data. It measured particles, magnetic fields, and plasma waves. recording how the surrounding environment changed as the spacecraft traveled from a region dominated by the Sun into one influenced by the galaxy. In a sense, Voyager did not photograph the edge of the solar system. It listened to the edge of the solar system through its remaining electronic senses, then quietly transmitted those numbers back to Earth, so humanity could reconstruct the shape of a boundary that cannot be seen with the naked eye. The edge of the solar system is therefore not where the story ends. It is where the story of the Sun merges with the larger story of the galaxy. And if humanity one day hopes to understand the environments of planets orbiting other stars, to learn how they are shielded from cosmic radiation, then our own heliosphere is the first lesson. Voyager opened that door with aging instruments, a power supply that grows weaker each year, and a journey that has lasted far longer than anyone originally expected. These discoveries have not only shown us where the solar wind begins to lose its dominance, but have also laid the foundation for every future mission that aims to travel beyond the heliosphere. If humanity one day launches a dedicated interstellar probe, that spacecraft will not begin from zero, because Voyager has already shown us how plasma, magnetic fields, cosmic rays, and turbulent boundary regions must be measured. Yet Voyager's 2 measurement points are still far too few to fully map the heliosphere, because a bubble that is stretched, distorted, and constantly changing with the solar cycle cannot be understood from only 2 cross-sections. For that reason, Voyager's data is both the first answer and a reminder that the Sun's boundary region still contains vast, unexplored spaces waiting to be discovered. But the farther Voyager traveled, the more its story shifted from exploration to survival. These 2 machines were never designed to last forever, even though they have already lived far beyond anyone's original expectations. The mission's power comes from radioisotope thermoelectric generators, where heat produced by the decay of plutonium-238 is converted into electricity to power scientific instruments and communication systems. This technology is remarkably durable because it contains almost no moving parts, yet it still follows an unavoidable limitation. Its power output gradually declines over time. Each year, the remaining electricity becomes a little weaker, forcing mission engineers to choose carefully between preserving one more measurement, shutting down another instrument, or sacrificing a portion of the spacecraft's heating system to extend the mission's life. In its early years, Voyager was a miniature flying laboratory, carrying cameras to photograph the planet, plasma instruments to study the flow of particles around the spacecraft, magnetometers to read the invisible structure of space, and sensors designed to detect cosmic rays, low-energy charged particles, plasma waves, and radiation in deep space. Time has gradually taken pieces of that system away. Voyager 1's cameras were shut down in 1990 after completing the Solar System family portrait, while Voyager 2's cameras ceased operation in late 1989 following its flyby of Neptune. Many other instruments were later placed into standby mode to conserve power, not because they had lost their scientific value, but because no machine can carry all of its senses forever into the darkness. In the final years of the mission, Voyager is no longer the spacecraft that sends back images capable of astonishing the world. Instead, it listens to the darkness with the instruments that remain. Magnetic field detectors, plasma wave instruments, cosmic ray sensors, and the faint measurements arriving from a place that almost no other mission has ever reached directly. A machine that once witnessed the storms of Jupiter, the delicate rings of Saturn, and the cold blue worlds of Uranus and Neptune now sends back little more than streams of numbers from interstellar space. That transformation did not happen through an explosion or a final warning alarm, but through one switch after another being turned off from Earth, 1 watt of electricity being preserved, and countless small decisions made to keep the mission alive just a little longer. Maintaining contact with Voyager is also unlike operating an ordinary spacecraft. At this distance, a radio signal is no longer an instant conversation, but more like a question sent into the darkness, followed by hours of waiting to learn whether an answer will return. If the command is correct, the system responds. If the antenna drifts off target, an aging instrument switches into an unexpected state, or part of the onboard computer processes something incorrectly, the silence can last much longer. The Deep Space Network must use enormous antennas on Earth to capture a radio stream so faint that it nearly dissolves into the background noise of space. What returns does not resemble a clear voice, but a whisper stretched across tens of billions of kilometers. That is why the spacecraft's main antenna must remain pointed toward Earth with extraordinary precision. Even a slight deviation can prevent information from reaching its destination. To maintain that orientation, the attitude control system must still rely on small thrusters. But those thrusters have aged along with the mission itself. Some fuel lines have accumulated deposits, certain heaters no longer perform as they once did, and engineers have had to switch between primary and backup systems to keep the star tracker and antenna properly aligned. This is a very different kind of engineering from the images commonly seen in science fiction films. No one can fly out and repair it by hand. No robotic arm can replace a failed component. And there is no rescue spacecraft waiting somewhere beyond. Everything is resolved through telemetry streams, decades-old documentation, the experience of mission operators, and extremely cautious commands transmitted through deep space. Voyager has responded with anomalous data. It has shifted its communication systems into unintended configurations. And it has returned error information that forced engineers to follow one clue after another to uncover the source of the problem. Incidents like these remind us that this mission is not an untouchable legend. It is a very real machine, growing old in a very distant place. And every time something goes wrong, people on Earth must repair it through reasoning rather than with their hands. Sometimes, what makes this story resonate is not merely the distance the two spacecraft have traveled, but the fact that there are still people listening to them. In control rooms on Earth, engineers continue to read the numbers transmitted by a mission that began in 1977. They monitor voltage levels, calculate temperature, track every subtle change, examine system status reports, and decide which instrument should be shut down next, so that the rest may survive a little longer. It is a very unusual relationship between humans and a machine. Voyager is only a piece of hardware, unaware of its place in history or the emotions its faint signals inspire back on Earth. But we are aware. That is why every year the mission continues to respond, feels like a piece of the past that has not yet fully left the present. When the two spacecraft were launched, the world was very different. The Cold War still cast its shadow over the space program. Personal computers had not yet entered everyday life. The internet had not become society's infrastructure. And many people still received news through television, read printed newspapers, and listened to music on magnetic tapes. Voyager has traveled through all of those changes. While humanity built the internet, sent robots to Mars, launched the Hubble Space Telescope, assembled the International Station, carried New Horizons to Pluto, and launched the James Webb Space Telescope to peer into the early universe, the two machines from 1977 continued their journey outward. And yet it was technology older than almost every modern icon that carried humanity's instruments into the interstellar environment first. That endurance did not come from a miracle. It came from redundant design, a stable nuclear power source, precisely calculated trajectories, a global ground communication network, and decades of work by engineers who refused to give up. Some decisions that seemed overly cautious in the 1970s have now become the very reason the mission is still alive. Backup. Systems allow the spacecraft to switch to alternative pathways when part of the system encounters trouble. Individual instruments can be shut down separately to conserve energy. Remote operating procedures enable teams on Earth to intervene, even though every command takes hours before the results can be seen. But no matter how careful humanity may be, physics does not negotiate. Plutonium-238 continues to decay. Electrical power continues to decline. Heat management continues to become more challenging. And eventually, the final scientific instruments will also fall silent. NASA has repeatedly faced the choice between preserving one more measurement today or saving enough energy for tomorrow. It is not an easy decision because every instrument that remains operational is studying an environment that almost no other mission can measure directly. The magnetometer reveals how the interstellar magnetic field changes around the spacecraft. The plasma wave subsystem listens to oscillations within the plasma, and Voyager 2's cosmic ray subsystem continues to record high-energy particles until diminishing power ultimately forces it into silence. Each remaining measurement channel is like a small window opened onto the space beyond the heliosphere. When one of those windows closes, we lose a way of seeing. That is why the measurements being collected today have become even more valuable. There is no guarantee that next year, Voyager will still return the same kinds of information, that an aging instrument will respond exactly as it did yesterday, or that the signal will always remain strong enough for the Deep Space Network to hear. Every packet of information returned during the mission's final years therefore carries the feeling of something that can never be repeated. It is science, but it is also time running out. When the final day of silence arrives, it will not be a sudden death, but more like a lamp slowly fading in a very distant room. On Earth, the antennas may still point toward the correct location, and engineers may still transmit commands. But eventually, no answer will come back. The data on magnetic fields, plasma oscillations, and the last information from the dark region through which the two spacecraft are traveling will end there. The scientific phase of Voyager will come to a close, but the journey will not. Yet the end of a mission's transmissions does not mean the end of what it leaves behind. Voyager's measurements continue to be used to refine models of the heliosphere. Compare observations from telescopes. Correlate data from spacecraft operating within the inner solar system, and support studies of the local interstellar environment. Every stream of numbers returned by the two spacecraft during their final years is like a rare specimen, gathered directly from a place that almost no other human-made instrument has ever visited. Even after the final signal disappears, that data will continue to be analyzed, re-examined, and incorporated into new models for many years to come. The two machines will continue drifting through the galaxy, quieter than any object humanity has ever created, yet still carrying the marks of the planet that launched them. And that is where the story shifts from science into something more difficult to define. Because Voyager carries more than scientific instruments, it also carries the golden record. A gold-plated disc mounted aboard both spacecraft containing sounds, images, greetings in many languages, music from different cultures, and basic information about where we came from. It was not an emergency message, nor was it a practical plan for finding extraterrestrial intelligence. No one can seriously claim that another civilization is certain to discover it. Yet the Golden Record remains one of the most profoundly human acts in the history of space exploration. When we sent Voyager outward, we were not only asking what exists in the universe. We were also leaving behind a small answer about ourselves. On that record are the sounds of ocean waves, the wind, a heartbeat, a newborn child, music, greetings, images of human beings, animals, nature, mathematics, and the location of Earth within the universe. All of it was placed aboard an object that will never return, may never be found, and may drift silently through the galaxy longer than the entire history of human civilization. But the fact that it exists says something important. For a brief moment in the history of the universe, a species living on a small planet became curious enough to send machines beyond the influence of its star, and gentle enough to place the sounds of home aboard them. Before Voyager became humanity's silent messenger, it turned back to look at Earth one final time. In 1990, after completing its planetary flybys, Voyager 1 was already far away and climbing out of the plane of the planet's orbits. At that distance, its cameras were no longer especially useful for planetary science, because there was no longer a Jupiter, a Saturn, or any nearby world ahead large enough to photograph in detail. But Carl Sagan and several members of the mission team championed a remarkable idea. Turn the cameras around, point them back toward the place Voyager had left behind, and capture a family portrait of the solar system. The maneuver was not simple because, from Voyager's position, Earth appeared very close to the Sun in the sky, and sunlight entering at the wrong angle could potentially damage the camera system. In the end, the mission team carried out the imaging sequence, and within one tiny frame, Earth appeared as a pale blue point suspended within a ray of light. There were no oceans, continents, white clouds, or any obvious sign that the entire history of humanity had unfolded there. Only a tiny point of light surrounded by darkness. Pale blue dot became one of the most famous images Voyager ever returned, not because it was beautiful in the way photographs of Saturn are beautiful, but because it forced viewers to change the scale of their thinking. Yet, that image carries another meaning when viewed alongside the measurements collected at the edge of the heliosphere. It shows that Earth is not only small in space, but also located deep within an invisible protective region created by the Sun. From that perspective, pale blue dot is not merely a portrait of our planet. It is also the image of a world enclosed within a shell of plasma that Voyager spent decades traveling toward. From the ground, Earth feels like everything. But from Voyager's vantage point, it is only a tiny speck of light suspended in an immense expanse. From there, the story becomes more than a famous photograph and connects directly to the invisible boundary region Voyager is now crossing. We do not simply live on a small planet. We live inside an invisible bubble created by the Sun, a place that contains atmospheres, oceans, life, memories, cities, voices, music, war, love, and everything humanity has ever called a world. Beyond that shell lies an environment that is larger, colder, and more diffuse, yet far from empty. Voyager traveled far enough to reveal that even the Sun has limits, that the star which seems to dominate our sky is actually blowing a region of influence into the galaxy, only for that influence to be compressed, bent, disturbed, and gradually fade away at the heliopause. There, the solar wind does not disappear like a light being switched off, but gradually weakens through a complex transition region where galactic particles become more abundant. Plasma conditions change, and magnetic fields behave far less simply than early models predicted. For that reason, Voyager's greatest discovery at the edge of the solar system was not merely that it entered interstellar space. More importantly, it revealed that the Sun's boundary possesses structure, motion, and ongoing interaction with the galaxy, and cannot be understood as a thin line surrounding the planets. After Voyager, the solar system was no longer a flat diagram with the Sun at the center, and the planets arranged in familiar order. Instead, it emerged as a system moving through the galaxy, surrounded by a vast shell of plasma that both protects the planets within and exposes them to the interstellar environment beyond. This is what allows Voyager's story to extend far beyond the spacecraft themselves. because it touches upon our true place in the universe. Earth does not drift alone through the darkness, but neither does it exist within an impregnable fortress. We live inside the sphere of influence of a star, and that star itself is only one traveler moving through the sea of matter that fills the Milky Way. Voyager helped humanity measure where that boundary begins, not through direct observation or a photograph, but through tiny measurements of particles, plasma, and magnetic fields, transmitted from farther away than any journey before it. Looking back on the entire story, what is most remarkable is not simply how long Voyager has survived, but how it changed the meaning of the word outside. Beyond Neptune is not merely darkness. Beyond the planetary orbits is not simply empty space. And beyond the heliopause is not the end of the story, but the place where the solar system begins to merge with the galaxy.
The heliosphere is not an end, but a transition.
One day, Voyager's final signal will fade away, but what it measured will remain within scientific models, research papers, the designs of future missions, and humanity's understanding of its home. Future generations may launch a new spacecraft that is faster, more powerful, and built specifically to study interstellar space, carrying superior plasma instruments, more sensitive magnetometers, stronger communication systems, and longer-lasting power sources. But when that spacecraft reaches the sun's outermost boundary, it will not be entering a complete blank unknown, because Voyager has already left the first markers behind. Those two aging machines showed us what to look for, what to measure, what to question, and how humble we must remain before a region of space that humanity once could only imagine from afar. That is the mission's true legacy. Not merely a distance record, breathtaking images of giant planets, or a golden record drifting through the galaxy, but the way Voyager expanded our definition of home. That home does not end at the atmosphere, the orbit of the Moon, or Neptune. It extends to the place where the solar wind weakens, galactic particles become more abundant, and the heliosphere gradually dissolves into the interstellar environment. From that perspective, Earth does not become smaller in the sense of losing significance. It becomes more precious. Because everything we know, everyone we love, every story ever told, and every dream ever launched toward the sky began from that tiny blue dot. Voyager traveled far enough to measure the boundary of the sun, yet somehow it also helped us see Earth more clearly. Thank you for joining Astrexo all the way to the end of this journey. If this video helped you see Voyager, the Sun, and Earth from a different perspective, be sure to leave a like, share your thoughts in the comments, and subscribe to the channel to continue exploring even greater stories of the universe with Astrexo. Your support helps us create journeys that are deeper, more accurate, and filled with even greater wonder.